afternoon with Ian O'Hara, who's the Deputy Dean, Faculty of Engineering at Queensland University of Tech, on the Growing Australia's Bioeconomy report. So Ian, are you good to start off?
Yeah, thanks, Georgie. Let me just quickly share my screen. Let me know when you can see it.
We've got it in the PowerPoint version, just not in the presenter mode. There it is.
Should be. Yep. Okay, good. Look, thanks, Georgie. Thanks, Shannon, for the chance to speak this afternoon. Actually, really excited to be part of this panel. It's really looking forward to listening to the other speakers. It sounds like it's going to be a really good panel. So what I'm doing today is talking about a report that we recently released called Growing Australia's Bioeconomy. And I would just I'd like to start by acknowledging my co-authors, Maddie Smith and Jerome Ramirez from QUT. They've done an amazing job in working on this report with me, and we're really pleased that we were able to release this report just a couple of weeks ago. What we wanted to try and do with this report was there's a lot of momentum happening internationally in bioeconomy. I'm sure that people are hearing and reading reports from around the world on all the work that's going on. What we really wanted to do was to try to present an Australian version. If we start to think about what a bioeconomy might mean for Australia, what does that look like? How do we think about bioeconomy in Australia? What are the key areas that we need to think about and need to start to prioritise within that? So just starting off, I mean, looking at some of the sort of global projections on bioeconomy, the estimates are that somewhere around $4 trillion of GDP is currently, the bioeconomy is worth around $4 trillion US dollars, but projected to grow to about $30 trillion by 2050, which would represent something like about 1/3 of total global economic value. Now that's massive. In that context, it means that there's massive growth in this opportunity, and there's certainly an opportunity for Australia to be a big part of it. When we look at what that means economically around the various countries, many countries have done economic estimates. The European Union, as an example, estimates that over 17 million jobs back in 2021 were in the current bioeconomy, let alone what the bioeconomy might grow to. Likewise, in Germany, well over 2 million jobs. Around the ASEAN nations, around 8% of the total workforce is currently in the bioeconomy, when we count things like agriculture, food, and some of the bioeconomy resources sectors. China estimates that their bioeconomy is worth something around 22 trillion Chinese yuan. And in the USA, again, around about 5% of their GDP is currently bioeconomy. So the bioeconomy is a significant part of the global economy today and is projected to grow very rapidly over the next few years. Now, what's driving this big change? Well, actually, one of the drivers is the innovation. So we're seeing artificial intelligence, machine learning, biotechnology innovation, the rapid progress in digitization, precision ag, really making agriculture and biomanufacturing much more efficient. At the same time, we're seeing customer demand increasing. We're seeing governments really stepping up with policies and in a range of targets across sustainability and economic drivers, regional development. So innovation, not just in science, but innovation in policy, is also helping to drive it as well. And of course, there are the big global drivers on reducing carbon emissions, better use of waste, better use of resources, etc. Now, these trends are all going to continue to increase. Science is only going to continue to progress. Some of the policy targets around the world are going to continue to increase. So we need to think about what Australia will be doing also to ensure that we stay abreast of these rapid change. Of course, the benefits of the bioeconomy are profound. We're talking about growing new biomanufacturing sectors, increasing economic growth, increasing economic diversity and complexity. And of course, that builds resilience into an economy. It benefits not just future industries, but existing industries, unlocks sovereign manufacturing, and unlocks waves of new innovation. And of course, environmental benefits and carbon emission reductions and social benefits in a range of areas, including jobs that will be resilient in the future economy. and strengthens regional and rural communities. So lots of opportunity globally, lots of opportunity for Australia as well. So what our report really tried to do was to say, well, within the context of all of the things that bioeconomy could be, what are the things that are really important for Australia? What are those opportunities that Australia can grab onto? And we actually came up with 8 priority sectors that we believe bioeconomy already does and will continue to play a big role in and continue to grow. And the top on the top line are really the ones where already a lot of progress is being made in the area of industrial biomanufacturing, in looking at how we can value add to primary industries, and there's quite a bit of work going on across a number of sectors to look at how we can better value add to the economy of agriculture. And of course, today what we're really focused on is the low carbon liquid fuels and sustainable aviation fuels area, and I'll talk a bit more about that just over the next couple of slides. But in other areas, there's opportunities to produce new food ingredients through things like precision fermentation, renewable gases, a lot of momentum in Australia in this space as well. In the waste to value, better utilisation of our waste resources is critically important. But then there's a couple of new and emerging sectors, the opportunity to grow carbon, nature and biodiversity markets over the next few decades. And if we start early, the opportunity for Australia to be a leader in bioeconomy equipment, technology and services. So much like in the mining and resources sector, the MET sector is now really a very significant part of the economy. We would hope that one day the MET sector will also be a really important growth opportunity for us as well. So taking that the jobs and skills beyond the straight biomanufacturing and exporting a range of services from this sector as well. So today we're talking about low carbon liquid fuels. And I've just got a couple of slides just to set the scene a little bit for this. So obviously in the bioeconomy, the chance to use renewable, sustainable, biological resources to produce fuels is something we've been doing globally for 50 years. But there's a real opportunity now for sectors like aviation, marine, rail, heavy transport. And the growth opportunities are really being driven by the need to reduce our reliance on fuel imports and the opportunity for us to grow that to renewable energy infrastructure as a nation. So why low carbon fuels and SAF now? As a number of recent reports have shown, imports of total refined fuels in Australia has increased from around about 30% of our total fuels to over 80% since 2010. So it's only 15 years. We've gone from being largely self-sufficient in refined fuels to really being quite at risk in terms of our fuel production capacity. There are a few alternate solutions, as we all know, for the hard to decarbonise sectors like aviation. And that will continue to be true well beyond 2050. The vast increase in fuel imports is having impacts on balance of trade, dramatically impacting on fuel security, and also impacting our economic resilience. We've been fortunate that technology risks around the world are being reduced through that international experience. But we don't want to leave it too long before we start to also take on some of the economic opportunities by being an early mover in the sustainable aviation fuels area. And of course, there are clear markets for products in Australia and overseas. The recent Clean Energy Finance Corporation report, the Refined Ambitions report, that I'm sure everybody on this call has read, identified current production infrastructure and announced projects around Australia. And this is a really fabulous map that shows the range of projects across every state in Australia. It shows the national opportunity, the national impact that sustainable aviation fuels and low carbon fuels could have. And of course, it would be remiss of me not to comment on the fact that actually Queensland is really driving a lot of project development at the moment, and it's really great to see that those projects continue to develop, not just in Queensland but around Australia. So as part of this program, we did look at what were the barriers and challenges, and we identified 4 key barriers: the absence of a cohesive national bioeconomy strategy. And of course, in some of those subsectors like sustainable aviation fuels, there's still work to do in the strategy and policy space as well. We need to continue to work on feedstock supply chains. We need to address those gaps between early stage development and commercialisation, and we need to address workforce skill shortages. So I think this is one of my final slides. What we really wanted to highlight were the recommendations. The report's available for you to read, but our recommendations were that Australia really needs to think about how we develop that national strategy in bioeconomy, but also in each of those subsectors, in sustainable fuels, in renewable gases, and other areas. What's that suite of strategy and policy that helps to unlock this opportunity? We need to continue to cultivate world-class economic and scalable feedstocks. So understanding what we have now, how do we liberate that, but how do we also grow future feedstocks to grow and scale the sector? How do we build the infrastructure to scale bioeconomy solutions? We work closely with companies like Mercurius Biorefining to demonstrate their technology at scale, and now there are opportunities for Australia to demonstrate other technologies as well. And finally, to grow the bioeconomy workforce skills and to continue to invest while we develop policy, but to continue to invest in research, development, and commercial translation. So for those who want to read the report, click on the link, scan the code. You're very welcome to access the report, and please reach out if you've got any comments or questions. And I would like to acknowledge our key participants and partners, the ARC Centre of Excellence in Synthetic Biology, Bioenergy Australia, and Sugar Research Australia. And thank you very much. I'm really looking forward to the rest of the presentations. Thank you. Thanks, Georgie.
Thanks, Ian. Next up, we have Samantha Michaux, the team lead of business development for Interac. Samantha, are you good to join on?
Yes, I'm here.
Hi,
Hi,
Samantha.
good morning. So let me take the presentation. Okay. Can you see my screen?
Yes, we can.
Okay, perfect. So thank you very much for inviting me. I'm really happy to be here and presenting you Ineratech. So we are a German company located in the southwest of Germany, founded 2016, so almost 10 years. Next year we are celebrating our 10th anniversary, growing very rapidly, almost reaching now 150 fuel time equivalent, and we keep on growing. So we are the e-fuel company from Germany. I'm going to present you who we are and also our strategy, our strategy towards the market ramp up of e-SAF, so e-fuel, e-SAF, so synthetic kerosene. So what we do basically, we take green hydrogen combined to carbon dioxide, and we turn it into high value waxes and synthetic crude oil, which are following an upgrading step turned to e-SAF, but also to other synthetic fuels. I'm going to tell a little bit more about that first of a time. We are a technology provider, mainly focusing on the synthesis of the chemical process, having our proprietary technology, which are reverse water gas shift reactor and a Fischer-Tropsch module, and shortly also developed a module for the upgrading to e-SAF and e-diesel. So we are mainly focusing on the synthesis and the upgrading and the distribution of the fuel. So mainly active in the downstream value chain. We used to work with partners who are selling or delivering us the green hydrogen and the CO2. The CO2, technically, we can take any source of CO2. So CO2 is CO2. So it can be coming from industrial processes or biogenic point source, or of course, direct air capture. However, the price for the CO2 from direct air capture is still very high. So it's not the favored feedstock for us at the moment. So we turn the hydrogen and the CO2 first into syngas using our reverse water gas shift reactor, which is then turned into a second step through a Fischer-Tropsch reactor, which is also a proprietary technology to turn into a crude and waxes, which are basically byproducts. The waxes can be either used as a byproduct to be turned to cosmetic or other chemicals. So the waxes can be sold directly to those industries, which turn them into other final products. Even in the food industry, we have discovered there are applications for our waxes. We have, for example, a customer who's using our waxes to produce vegan butter. So they are actually using the synthetic wax and turn them into fatty acids, which believe me, the butter tastes like real butter. So because I'm not a vegan person, so I had my concerns, but really it tastes the same and it's really good. The crude and the waxes can be also turned through an upgrading process to eSAF, e-naphtha, and e-diesel, which can be one-to-one used into the existing vehicle motors. So this is the advantage of synthetic fuels, is that the off-takers do not need to replace any of their fleet. They can replace the fossil fuels one-to-one with our synthetic fuels. So what is so special with our technology? I mean, Fischer-Tropsch reverse water gas shift is nothing new. It exists for more than 100 years now. But we have designed actually a completely new reactor, which allows us to make them more compact. So 80 times more compact, twice more efficient, with a high conversion and enhanced heat recuperation. But particularly, our synthesis or reactor, which are included in our synthesis modules, are load flexible, which is very practical when you work with renewable power. So that means that even if you have a fluctuating renewable energy supply, we can keep the plants operating at a minimal load, which allows us to keep the production running. It's also an advantage regarding the maintenance, because by being modular, our reactors can be switched off. So some reactors group can be then shut down to be maintained, while others are being kept operating. And this way you can keep your production running at a minimal load, but still running. So we have achieved our biggest milestone now. So we have built our own e-fuel plant in Frankfurt that start the production in May this year. So I think the best is maybe to let you discovering our plant. So here a nice picture which shows the modular approach of our plant. You have a big module and two small modules, as you can see on the right side. This allows us easy scaling up of the plant, because you know the availability of green feedstock is today still limited. So our advantage is that we can start small, and as soon as we have more feedstock available, we just add additional module following a numbering up approach. So here in Frankfurt, for example, we have a big module on the left side. It's a 5 megawatt module, 5 megawatt electrolysis capacity, plus two 1 megawatt module, which aims to a 7 megawatt plant. With a 7 megawatt plant, you can produce up to 2,500 ton e-fuels yearly. So what we did here, it was exactly the situation. We had limited available CO2, biogenic CO2 coming from a biogas directly on site, and green hydrogen from a chlor-alkali production. and the volume of the feedstock were limited. So that's why originally we have been developing a concept of 10 megawatt, and we had to downscale because the availability of feedstock was limited. So this is an advantage today because this means that you can easily scale up your plant as soon as your feedstock are available. And this way, by having also a standard design of our module, we just add, following the legal principle, just add additional module to scale up the plants. In Frankfurt, we are producing e-kerosene, e-diesel, e-naphtha, but also waxes. Let me sharing this video with you. Then you can discover the start of the production of the plant with the first drop of e-fuels, which has been delivered 2 months ago.
The first e-fuels from Eneratech's Pioneer plant are here. Our Pioneer plant in Frankfurt has started operation, and with that, the very first drops of e-fuels and e-wax are flowing. What begins with a single drop marks the start of the next era, an era where climate-neutral fuels and waxes are no longer a vision but reality. After startup, the commissioning lead hands over the symbolic first drop to the site manager, who will lead operation from now on. These first e-fuels and e-waxes will be stored in our on-site tanks, getting ready for first delivery. Watch as the first bottle of e-fuel is freshly tapped at the plant, a meaningful symbol for what's to come.
So how does our scale-up strategy looks like? Of course, Frankfurt with a production capacity of 2,500 tons, it's a lot, but at the same time, it's nothing considering the global demand. So this was our first of a kind plant, a break-even plant. Now we are planning the next commercial plants, primarily in Europe, targeting a capacity of around 25 megawatt of electrolysis capacity. So it's about between 8 to 10,000 ton e-fuels yearly. But we are also already working on the commercial rollout with the design of the bigger plants, targeting a capacity of 30 up to 40,000 ton yearly. So this is the equivalent of 100 megawatt electrolysis capacity. So for example, targeting Australia would be such concept of a big scale plant. This is, for example, a 50,000 ton e-fuel production that a design we have developed originally for Chile, but this would be also a concept that we could apply easily in Australia. This is relying on a greenfield concept, so you have everything on site, the electrolysis, the synthesis, the water treatment statement, you have the power park, also the upgrading, so you can produce everything on site and directly deliver your eSAF to your customers at proximity. So, and this is Era 1, the first e-fuel plant in operation currently in Europe. Oh, that's all.
Thanks, Samantha. Next up, we've got Max Thusbaß, the Junior Project Assistant for Casino. Max, do we have you on the line?
I'm here, yes, thank you.
Hi, Max.
I will share my screen. Okay, first of all, thank you, Georgie, and to all of Bioenergy Australia for organizing this meeting today. We were really looking forward to it, and we hope you like what you hear from our side today. First of all, Cafenia, our mission is to become the global technology leader for SAF, for SAF production and renewable fuels. For that, we have founded our company in the year of 2018. We are currently having 2 offices, one in Bernau and one in Frankfurt. The one in Frankfurt is also where our pilot plant is currently constructed. With that pilot plant, you can see a model of it in the middle. We are able to produce renewable fuels, SAF, biodiesel, methanol, and it's based on the newest plasma-based technology. For that, we already have a bit of history. We started in 2011 as CCP and got into cooperation with Lufthansa, the German national airline, for the R&D for the development process. Yeah. Due to economic difficulties, Lufthansa had to exit the cooperation agreement in 2017, which led us to found our company today, Cafenia. And as you can see in the rest of the timeline, we have secured a lot of funding and investments for building our pilot plant and supporting our development of the company. Our technology itself is actually pretty basic. Yeah, we only need 4 feedstocks. First is the renewable electricity, then we have the CO2 and the methane. The CO2 and methane we can get both by biogas. And the last ingredient is water. With those 4 ingredients, we are capable of producing syngas. Our reactor is only producing syngas, and that syngas will then be used in a later process via the Fischer-Tropsch synthesis, via the process, which then we can produce SAF, diesel, naphtha. Also, we have the option of a methanol process, for methanol technology, but we are not focusing on that. But it's also a possible way to use syngas. Here you can see our reactor or the chemical processes inside. Technically saying, each of these 3 processes are nothing new. They are well established and well known for years, if not decades. The speciality about our reactor is that we are the first of its kind to develop a reactor which has all 3 processes combined in one reactor, which we can then use to produce our lovely syngas. Our reactor is also pretty modern constructed. Yeah? You can see on the left side, which is our PBR reactor, the plasma boudoir reactor. We have all ingredients going in, all ingredients going into the reactor will come out at the end. We have 100% selectivity in our process. Compared to regular PTL processes, which are currently established, you always have some kind of waste products like oxygen or water. That is the advantage of our reactor. We use 100% of everything that's coming in. But with that said, we also have a power efficiency of 86% compared to 45% efficiency in regular PTL processes from what we have seen so far in our research. How do we achieve this 86% efficiency? In our reactor, the plasma zone is at the top, and the heat produced at the top will then be used in will be reused in each process of these. So that's the advantage of combining all these 3 processes, so we can use the heat produced once. With that said, we have a bit of a competitive advantage. Our SAF production has a CO2 reduction of 92%, higher than any other fuel route we have found so far. As I mentioned before, the 100% selectivity, we have no material loss and less energy loss thanks to our modern design. And with the 86% efficiency, another advantage is our very high feedstock availability. Technically, we only need electricity, we need biogas, and we need water. Depending on the scale, we have to add a bit of CO2, but that's depending. Another advantage of our modern technology is the upscaling options. We have 2 options. For once, we have the option to scale up in numbers. You can see here on the left side, it's one PBR reactor. It's a 5K reactor, which is capable of producing 5,000 tons of syngas each year. After that, you're free to also add another reactors. You can scale it up to 100,000 tons, which is very energy efficient. And the second option is we are capable to scale in size. The advantage here is that our regular 5K reactor, which you can see on the left side, you just change the diameter by a few centimeters and you can scale up to almost 10 times more production. That's the advantage of our technology, but just changing the diameter of the reactor. I gotta be open with you, the 50K reactor is not yet available. We are still in process of researching and developing that kind of reactor. Also due to the reason because we are still building our pilot plant in Frankfurt. Then the technology itself, we were very keen from the start to patent the technology all over the globe. You can see here 253 patents globally has been granted, and we are ongoing to make it even more. Then looking at our partners, we once have partners also for the project implementation and development, and also for research and development, which are mostly universities and research institutions, but also some engineering companies who are in the development industry. On the left side, most noteworthy are Lugresta. Lugresta is currently building one of the biggest biogas plants in China with a 16 megawatt biogas plant. They are our partners for everything related to the biogas purchases and the build up of a biogas plant, because our reactor is capable of using gas once from the grid system and also from biogas plants. We can use the grid system, which is usually filled only with fossil gas, but once in Germany, we have the option to make balance sheet purchasing, meaning that we can buy biogas in the north of Germany, but still use the fossil fuels from the south. But as you probably know, SAF needs to be renewable and sustainable. Therefore, we have to use biogas. The next partner here is Emerging Fuel Technology. They have the most patents in the world when it comes to the Fischer-Tropsch technologies. We are working very close with them. Our directors are very close with the CEO of EFT. They will provide the Fischer-Tropsch and the hydrocracker, which will then later be used to transform the syngas into SAF. Then, some key facts about our first plant. As I mentioned before, we are currently building our first plant in Frankfurt. The construction will end in about a month, and then what we will do for the rest of the year is just a bit of fine adjusting to make the plant run as smoothly and efficient as it is. Once that is done, we have already started a couple other projects. We have a lot of interests in other locations. Once that is completely done, we will go into commercial production, which we are currently on the best way to do that. Here on the right side, you can also see in Frankfurt on how our reactor looks today. Sadly, you can't see the inside, but we have a 3D rendering model from the inside, so you have an idea of how it will look like. Then, talking about our project in Australia, we called it AusSAF. We want to bring a PBR reactor to Australia. We have been in contact with a lot of organizations already, including Bioenergy Australia, Qantas, but also Austrade. which are currently our contacts for consulting and networking. Our next step is to conduct a feasibility study to determine the best locations. You can see here 6 spots which we are currently looking at, but they will be much more by the end of the year. We are planning to start the feasibility study in early 2026. Till then, we are trying to build awareness and to expand our network. We are currently in the process of securing funds and investment. We are in contact with a couple investment firms already. And as I said before, we also have the option of building a biogas plant. According to our contacts in Australia so far, the ambitions to build up the biogas industry in Australia are very high currently, and that provides a perfect opportunity for us to look at the feedstock routes. For that, we are also using the next couple of weeks and months to add to our team another partner who will do the feedstock research and supply chain identification for us. We already have 2 partners you may have heard already. One is Gerard Couts and Associates, who is our partner for real estate development, and we are also in partnership with Argi, the Aviation group in Australia, which is also connecting us with several investors and doing some regulatory topics for us. The long-term goal is to found an own entity, Cafenia in Australia. Once we have done that, we will start doing the feasibility study. And on the right side, you can already see also Shannon and Shahana McKenzie from Bioenergy Australia and some others have already visited our pilot plant in Frankfurt. I hope you all enjoyed it. And yeah, that being said, that's already the end. If you have any more questions, please don't hesitate to contact me, or you can go to our website. If you want to know a bit more about the details, we have a white paper there, which you can download. You will learn a bit more about the technology and also the history of our company. That said, that's it for now. Thank you for your attention. If you have any questions, you can reach out to me after the meeting. Thank you.
Thanks, Max. Next up, we've got Dan Moloney, the EPV Projects and Technology for Gadara Energy.
Good afternoon, everyone. Is my presentation on screen, Georgie?
Yes, it is.
All right. Thank you for the opportunity to talk today. Fascinating presentation so far. I think what's clear from the previous presentations, as Ian outlined, is the enormous opportunity for biomass and waste to be a feedstock for fuels. And what you've heard from Samantha and from Max is the different technologies, and the technologies in the energy transition, what we're finding, it's not an either or, it's an and. There's, depending on the feedstocks, depending on the scale, there's multitudes of different technologies that suit that application. What's really interesting today is you see the commonality of syngas. Ways to create syngas plugs into the existing infrastructure where, syngas can be applied to many different applications to create fuels. So we're really utilizing a lot of existing technology. What we're changing is the front end. And Gadara is exactly the same. What we look at is waste as a feedstock, particularly solid waste. Now, solid waste is a broad category. It's municipal solid waste right through to agricultural waste. And, there's a vast amount of that feedstock in the world. The current global production is about 2 billion tons of waste per annum. This is forecast to double in the next 30 years. So as population grows, as consumption grows. Australia is responsible for about 75 million tons of that waste. That's largely municipal waste, but a large quantity in Australia is the waste from agricultural production. With this, depending on technologies, you could, and particularly say if you applied our waste gasification technology, you could fuel 100 million trucks. You could fuel up to 9 million long-haul flights. So the potential for the use of waste is enormous. As well as the abundant feedstock, there is a demand which is creating an economic case for these facilities. If you looked at the global SAF demand out to 2050, and this is our analysis based on government mandates, particularly say Europe, UK, intentions in USA, China, etc., and the global and airline commitments, the global SAF demand is going to be about 360 million tons a year by 2050. The existing and announced supply, which is largely driven by animal vegetable fats, can only satisfy about 15-20% of that, and there's a limit to that feedstock. So where does the gap get filled? And this is where I believe technologies like waste gasification can substantially fill a large part of that gap. You see a similar case in methanol. Methanol is a drop into fuel. It's a chemical building block. Increasingly, you've seen a real increase in demand projections from the recent International Maritime Organization regulations on sustainable fuels. So shipping particularly is driving the global methanol market. We've certainly seen an uptick in potential developments in that area as well in recent months. What we do is we own the only commercially scale proven technology to gasify waste. Gasification, like the previous speakers have mentioned, technologies have been around for a long time. Gasification is over 100 years old, but being primarily applied to coal. So there's a lot of knowledge from that industry. However, what we do is we gasify waste. And this can be all sorts of waste. We can take forestry, agricultural waste. So this would, from forestry would be sawdust, trimmings, bark. Agricultural waste, things like corn stovers, rice husks, etc. We try and avoid using the agricultural products that would go into the food chain. We don't think that's particularly sustainable. So what we'll look at is the waste rather than virgin wood or virgin agricultural products. We can also work with municipal solid waste. Now, around the world, there's a huge issue with landfills and incineration. You see increasingly landfills being banned, and incineration also causes environmental issues. So increasingly we're recycling waste. So typically waste management companies, they'll extract the valuables like metals from the waste. They will typically divert the organics into biodigestion route. They may take out glass, etc. What you're left with is really a mix of textiles, plastics, paper, foils, etc. That's generally termed refuse-derived fuel, and that's an area that currently typically gets incinerated or landfilled. What we do with that is we gasify it. We bring it into the gasifier. The gasifier works at high temperatures, 900 degrees plus, and it works at pressure. And this breaks the waste and down to its constituent molecules. So again, we're going back to those carbon, hydrogen molecules, and creates a syngas. And like the previous speakers discussed, once you have syngas, you have a building block for many sorts of sustainable fuels. Whether that's methanol through the Fischer-Tropsch process. I was interested, Ian mentioned the renewable natural gas, so methanation, and all these end products are increasing demand for regulations and increasingly economic to produce, and that's key. A lot of these technologies have been around for a long time. What we're seeing now is it's becoming economic to apply these technologies to create fuels. The advantage of our technology is it's proven. This is technology was actually started operation in the 1980s, 1990s in Germany. Sponsored by the German government, and it resulted in commercial scale plants, typically 500 tons a day in a single gas input waste to a single gasifier. creating methanol. There was plants built which were creating syngas for power, plants built for biomass to ammonia. So a wide variety of applications. When you're gasifying or treating waste feedstocks, one of the challenges, the waste itself is made of many things. So there's impurities in the feedstock. And one of the keys to get a stable, usable syngas molecule for fuels and chemicals is converting those impurities. And that's where you need an oxygen-blown gasifier. So there's a lot of gasification technologies out there, but really to get a fuel-grade molecule of syngas, you need to have oxygen blown, and our system is oxygen blown. The other thing is these facilities need to be built at scale. So our entry point is 500 tons a day. We also have a 1,000 ton a day input unit. Like the previous speakers, then we'd build multiple trains as required. But to get economies of scale, the gasification system needs to be pressurized, and our system is pressurized to 15 bar or more. What that does is it ensures you're creating enough syngas to build a complete facility that is economically viable. This is what a facility would typically look like, and I think you're going to hear shortly a great example in Australia. But typically the non-recyclable waste, and this is waste that is not recycled at the moment, and that can be biomass or agricultural waste, it can be municipal waste. It gets sorted in existing waste management facilities, shredded, and we pelletize it. The pellets are quite small, about 20 millimeters or 2 centimeters long, about half a centimeter wide. That makes it easier to transport and store the waste material. It also homogenizes the waste, so you get a more predictable syngas out. As I said, we gasify it. The syngas treatment then is typical syngas treatment. So from the fossil fuel industry, there's a lot of established technologies on how you clean up the syngas. And once you had a clean syngas, you can go to methanol, again, by established fossil fuel processes. You can go, as previous speakers mentioned, through Fischer-Tropsch to hydroprocessing to SAF. There's emerging methanol to SAF technologies. A number of technology providers of some of the big name technology houses are working on that technology, and will probably start coming online the next couple of years. So that gives you optionality. With a methanol route, you can sell to methanol to chemical producers. You can sell to road fuel off-takers, you can sell to shippers, but you could also potentially then expand later into to jet. And increasingly what we see is green hydrogen. The energy transition really is the coming together of a combination of technologies and trying to maximize production. Green hydrogen is becoming a major driver in that. You particularly see locations where there's abundant solar, there's a potential for wind power or hydro. The cost of electrolyzers is coming down rapidly, and the cost of green hydrogen is coming down equally rapidly. Once you have green hydrogen, you can boost the production of SAF or methanol from the same amount of feedstock by up to 2 times. And that's making a huge difference to the economics of these facilities. So I think particularly in places like Australia, where you have abundant potential waste feedstocks and abundant potential for wind and solar, the green hydrogen opportunity will make a significant difference and probably create a cost of production that is extremely competitive on a global level. So I think the opportunity for Australia is immense. It's taking a lot of proven technologies. The key here is integration of those technologies. Most of these technologies are high technology readiness levels, talking 7, 8, 9. The key is integrating them and making sure they all work together. And that's where we work with a lot of our partners. We provide licensed technology. So we license this technology out to developers, to investors. I would also note that we're part of ARA Partners, which is US private equity solely dedicated to decarbonization. They own about 30 companies of all sorts of technologies and platforms. But the key is they're all scalable, they're all repeatable, and they can be, they're portable, again, similar to previous speakers. So I appreciate your time today. I think the Australian market has enormous potential, and look forward to hopefully connecting with you after this meeting.
Thanks, Dan. Appreciate that. So we've got about one more speaker left, so it's about 10 minutes with the last speaker. I know we might just run over a little bit of time, but great to have David Stribley, the Executive Director of Hammer Energy.
Hi, Georgie, you can hear me all right?
I can hear you.
Great, I will share my screen, hopefully. There we go. So I'm conscious we've got 6 minutes. Hopefully you can all see that.
Yep, that's all good.
Great. So thanks. Hopefully a good segue there from Dan. So let me just jump straight into it about Hammer Energy and what we do. So Hammer Energy, hopefully that's changing the screens, but Hammer Energy is a pure play project developer and low carbon liquid fuels company. So I'll jump on to the next one. Sorry. And I guess to start with, our vision is a world where the sea and the skies are powered by low carbon liquid fuels. And that's probably not dissimilar to a lot of the people on the call here. Hammer Energy was formed originally by largely coming out of oil and gas and really wanting to accelerate the adoption of these low carbon liquid fuels. As you just heard from Dan, a lot of the technology is actually highly ready. And a lot of this now is about how do we commercialize it and actually turn it from where it is today into commercial projects. And that's what Hammer Energy does. Part of that, as I said, we are a platform developer and we work across the whole supply chain, working closely with customers across both aviation and the maritime sectors. We've really focused on everything from the biomass feedstock all the way through to the end customer. So today I'll share a little bit about the methanol to jet process that we've been working on and recently announced the completion of a feasibility study on that. But we also have our flagship project, which is a green methanol development, which is using gasification, very similar to what Dan just ran through there with Gadara. We are a group of engineers, predominantly hailing out of oil and gas. And we really believe that actually gaining scale in this sector is really important. These are large chemical facilities. Scale is crucial in how we bring down the cost and get to that minimum viable product ultimately. We do have a pipeline of projects. I'll explain a little bit more about Portland, but predominantly today we'll spend most of our time exploring methanol to jet and why we think that has a unique opportunity in Australia to support the aviation industry from decarbonising. So, methanol to jet. There are a number of suppliers of methanol to jet technology in the market today. But if we just step through from the left-hand side there, we are looking at a process here where we at Hammer are working on forestry residues, gasifying that product and producing methanol. We believe that creating this intermediary product allows us to co-locate our gasification or methanol process near where the biomass is or the renewable power, and then producing the methanol to jet where the ultimate customer is, which generally are in major cities. So that allows us to transport the methanol to those locations. The methanol to jet process, it's really a combination of a number of different processes. So you can see the three that are mentioned there, all of which have been commercialized at scale, particularly throughout China. And as Dan pointed out, a lot of this is about how do we actually stitch together the pieces of technology to bring these to reality. We're also working very closely with shipping customers. We believe that commercializing through this pathway actually allows to de-risk a lot of the aspects to these projects by having multiple pathways that we can ultimately supply our methanol to. This is probably the main slide I'll touch on here. By no means is this a comprehensive sort of checklist here. And I've only thrown up here a couple of examples of methanol SAF production pathways. I have excluded the waste oils pathway here. But if we just step through here, some of the benefits we believe, particularly for Australia and looking at methanol to jet, is the feedstock flexibility. We can use all sorts of different feedstock from CO2, which we saw earlier on in the discussion, to get syngas and go through to methanol. We may choose to do that where we have a CO2 source and good renewable power. We can use waste feedstock in major cities, and we can use biomass where we are in regional areas. The benefit of that is we can produce methanol from multiple ways, but that gives us the ability to then scale our methanol to jet process. Fischer-Tropsch has a similar pathway there. I've oranged here ethanol, that it has less flexibility, though it does have flexibility as well. In terms of maturity, in terms of as a SAF pathway, methanol to jet is yet to be ASTM approved. We expect that will happen towards the end of this year, but it is an emerging technology around the TRL process here, compared to Fischer-Tropsch, and I'd even say ethanol to jet is a little bit ahead there as well. One of the key things for us when we look at these processes is ultimately we believe that the carbon is actually the resource here, and we need to make sure we use every one of those carbon molecules that we bring into the front end of these facilities in the most efficient pathway. Methanol to jet is slightly more efficient through that pathway. If we look at the energy efficiency, we could argue around the different points here. Some are a little bit more than the others, but ultimately we believe that how you integrate these processes into a combined plant is probably what will lead to the greatest gains in energy efficiency. We do believe that from a commercial flexibility, having that methanol intermediary does offer a large amount of flexibility. Fischer-Tropsch plants are generally going to be co-located with either existing refineries where they need to upgrade the syncrude, or they will need to be a single process all the way through. We won't hide from it. The total process is likely to be more expensive from a CapEx point of view around the methanol side of things. Gasification plants and the likes are expensive. But when we look at just the methanol to jet plant in itself, it will be very comparable to the other processes, particularly the ethanol to jet side of things. And the other thing that I think is really interesting and attractive for Australia from a methanol to jet side of things is ultimately the ability to phase and scale. We may start with what we're looking at, and that is Portland, and then going to methanol to jet in a major city. We can then phase that as more methanol processes come online. We look at this as really a hub and spoke model. And the beauty of this is this allows us to scale our overall SAF production as demand for the product changes, and allows us to ultimately bring down the cost of production. So as I said, we have recently completed a feasibility study. We are looking at 2 primary locations for the methanol to jet upgrading facility in major Southeast Australia cities. From that assessment, what we did find was vertically integrating a methanol to jet plant with the methanol production provides commercial flexibility, and it was an attractive way to make sustainable aviation fuel. It is a technically competitive pathway, and we do believe that Australia has a competitive advantage to go down this route when we compare it to other SAF production pathways looking forward. And as I said on the last page, we do feel it is and it was shown that it does offer a scalable and very future-focused pathway for SAF where we do see costs coming down. So that was very brief given the time, but thank you, and really enjoyed the discussion today, Georgie. Really good panel, so thank you.
Thanks, David, and thanks to all of our speakers for providing your time and insights this afternoon. It was great. I believe we'll be also circulating the recording from today's session around with members and those registered for the webinar. So look out for that one coming around. And thank you for our members for joining us this afternoon.
Thank you. Have a good day.
Thank you.
Thank you. Thank you.
Thank you, everyone.